I'm going to start off this video by first explaining that you have to make an adjustment in the microcap electronic analog simulator by going into the global settings that you can locate by depressing simultaneously three keys: the control key, the shift key, and the letter G key. And then you go into this value up here, and the default will be 1M, 1 milli. And you want to change it to either 1 or 3 nines and an M. It can be lowercase or uppercase. Doesn't make any difference. It means milli. And that'll make it possible to reduce the likelihood of getting matrices singular errors, although it won't eliminate it necessarily. It won't guarantee the elimination or avoidance of matrices singular errors, but it can reduce the likelihood to a very large degree. It all depends on how well you design the circuit. And there are other measures. When I say well, I mean there are other measures to take. So let's see if I can find the schematic. So, what happens is you get all these, 32 inductors within the octagon, so I call them octagonal inductors, and 16 octagonal capacitors. And you want to be certain that each one is unique from the other. Now, in the real world, when they are fabricated, there's always slight deviations, so you don't have to worry about it. But in the simulator, you got to worry about it, because they use floating point arithmetic, namely what I would call scientific notation, but whatever you call it, you only have so much accuracy, so many digits to the right of the decimal point, and I think it's one digit to the left, and then it'll be to the power of something, e to the 10 or e to the negative 20, whatever it happens to be. You start losing accuracy when the value of the number starts to become excessively large or excessively small. And that's a crucial problem, because when the simulator tries to approximate the outcome of a simulation, all it has to rely on are approximations. And since over unity, if it's not a regulated over unity, which this circuit is, will want to go to infinite oblivion eventually. The larger or the longer duration you take it, the larger the amplitude of the current and the voltage becomes, and before you know it, you get matrices singular error, sometimes earlier rather than later, depending on how poorly you design the circuit. So I go into each one and I modify the values of, I did it for the spark gaps. Every single spark gap has a slightly different, what I like to do is 1/10 of 1% deviation. Sometimes I might take it more than that, to 1% of 1% deviation. So if the capacitor in question has to be, let's say 1 microfarad, then instead of being 1 microfarad, I change it to 1.001 microfarad. And to help me keep track of everything, the deviation I make the same as the numeric value of the label. So if the capacitor is C20, then the deviation will, and it's supposed to be 1 microfarad, then the deviation, I'll reset it to 1.02 microfarads to indicate 20 parts per thousand of a microfarad unit that I'm deviating it upwards. Keep things simple and straightforward for myself. I'll do that for all the parameters inside of the neon bulb spark gaps, all of the capacitors, on all of the inductors. Now, this circuit is different than the last version in that I replaced all the diodes with inductors. Because I thought to myself, no, wait a minute, Eric Dollard would say this, and I should know better, but I guess I'm just a newbie. If you're getting nothing but voltage, and there are indications that it's dominated by capacitive reactance, then duh, shouldn't I bring in some inductors in the same kind of configurations analogous to Eric Dollard's analog computer? Yeah, so it just works out that way, that if I replace all the diodes with coils, because I already set it up that way to begin with, then I get a kind of analog computer, because I get coils facing each other, I get capacitors facing each other. Now here I have spark gaps facing each other and coils facing each other. So there in the middle zone, it's a little different. There are three different rings. There's an outer ring, a middle ring, and an inner ring, and then there's an empty spot in the middle. And the outer and the inner ring are more like Eric Dollard's analog computer in transverse electromagnetic mode. They're linked daisy chain in which the capacitors are in shunt and the inductors are in series. That's how a normal electrical engineer looks at a transmission line. Because if you go around the circle circumferentially to the center, all your inductors are in series and all your capacitors are in shunt. Now, when we come to the middle zone, again, it's about the same, because a spark gap is kind of like a capacitor part of the time, and the other part of the time it's a capacitor whose dielectric has broken down, and you get arcing through pinholes, leakages, through the dielectric barrier that's in the capacitor, which represents the arcing across the two electrodes of a spark gap. So in a sense, I still have a TEM module even in the middle zone here with the spark gaps and the coils. Oddly enough though, it's capacitive reactance that dominates this thing, not inductive reactance. So it's kind of a fascinating circuit. It's got all kinds of peculiarities to it. Now all the capacitors have 100 milliohms of equivalent series resistance, and that means I have to go and vary those as well as the capacitances of those capacitors, of all the capacitors. So I have a different one for each capacitor, no matter what the value of the capacitor is. It could be this one here that has a very large capacitance of 1.02 e to the 32. So I chose to vary the capacitance with a 0.02 on the numeric value. But its resistance is going to be something similar. Let's say it's 100.016 milliohms of equivalent series resistance. So it'll be something along those lines. Now, all of the inductors, I chose an arbitrary value of wire gauge of 25 because it just works out that, approximately speaking, when you have a magnetic winding using wire gauge 25 AWG, AWG, the resistance along that length of wire, the simple resistance, not the inductive resistance, but the straightforward resistance, when you coil it into a coil, the resistance, the simple resistance, is nearly equivalent to the inductance in units. So if you have a coil of 1 Henry, then the resistance will be 1 ohm. And it makes it really easy to figure out, okay, what kind of equivalent series, or what kind of series resistance should I put in my coils? Because I got to be realistic as much as I can. Doesn't mean the simulation is realistic, it just means I got to try to be realistic to make less work when it comes to building it, to try to figure out all the other details that were left out of the simulation that caused it to work fine under simulation. You know, you tweak it and you tune it and you hit this resonant sweet spot and you get over unity, and then you go and build it and you don't get anything, it sits there because you probably missed the tuning point, the sweet spot for resonance to occur. And you're going to have to start monkeying with it, but at least some of the work has broadly already been mapped out under simulation, and now you got to work out the details, which is going to take a lot more work. You know, just like it took me work, it's going to take the builder a lot of work. You know, so this is, you know, I didn't do anything for you. I just gave you, I'm just giving you a heads up over what may be possible if all the details are worked out when it comes time to build. I worked out as much as the generic archetypal problems of the overall look and feel of the thing. But the builder still's got to muck through a lot of variables that on its face I cannot solve for you, because this is not a build, this is just a simulation. So don't take it as a failure if when you build it nothing happens. I take the position that Edison took, because I'm no Tesla. I exhaust all options, and when I say all, I mean all. Just when you think your body is going to break down and along with your mind, that's when Edison was about to make his breakthrough if he didn't push himself beyond that point. And he realized, oh, I have to use tungsten for my filament in my incandescent bulb, after he'd already exhausted 10,000 other possibilities. So it's literally my game plan. Since I don't know what I'm doing, my game plan is exhaust myself in the course of exhausting all possibilities, because that's the only way to figure any of this out. Trust me, I knew nothing when I got started. And now I know a whole lot simply because I did the work, and it's a lot of work. So don't think that a free energy device, you're going to get off easy in that somebody's going to do it for you and figure it out. At least when it comes to me, no. Maybe somebody else will do everything for you. But when it comes to me, there's always work involved if you want to succeed. Time, work, money, and so I try to reduce the expense as much as I can by simulating it in advance of it being built. But that does not guarantee you're not going to waste a lot of time and money and effort and exhaustion trying to figure it out how to make your build work. So don't think, okay, so that's the caveat to free energy, is it's no free lunch. I'm trying to figure it out. All right, so now I got to back up. So that's one of the first images I wanted to show you. So now what I did, I went through 5 different tracings. I focused on, let's zoom in again. I focused on this capacitor and I labeled it. See, all the others I had the labeling so it doesn't get in the way, because it's kind of tight fit. But the only ones I need to focus on are 5 components. 2 components of here, I'm not interested in the spark gaps, what they're doing. But I am interested in 1 cap and 1 coil. So I chose this one, and it happens to be labeled C3, and this one happens to be labeled L29. I'm not too interested in this capacitor here, although you can, out of curiosity, you can find out what's going on in your own. But in the load area, that's what I'm interested in, and the aerial, or the ground, whatever you choose, however you choose to ground this thing, whether you stick your ground up in the air or stick it down in the earth. So I choose both coils. The results are going to be the same, even though the pre-charge is on 1 cap. Both caps are going to be the same. So I just arbitrarily chose coil 1 and cap 1. The cap 1 is 1.019 farads, and the coil is 1.0001 henries. So that's, I think, one of the few instances I actually took it to the 4th decimal position, to the right of the decimal point. Now the aerial has to be a low value of capacitance, the aerial component, because that protects the rest of the circuit from the loss of voltage leakage to ground. So you got to put that cap there to protect everything, and it has to be a very, very low value. It's the only one that's very low. How you get it to be that low? It can't be that hard. A low level capacitance means that the thickness of your dielectric material is very, very thick. It's the inverse. So a plate of glass you taken out of a picture frame is going to be in the femto range. It may not be 1 femto of farad capacitance, but it's certainly going to be less than 1 pico, much less. Now the best dielectric, of course, is a vacuum. And wouldn't you know it, Tesla is the person who invented the vacuum tube capacitor. He never commercialized it during his lifetime. It began to be commercialized a year before he died. And I'm pretty certain, I will take a guess estimate, that the Pierce-Arrow 1931 experiment or demonstration of his Pierce-Arrow electric car conversion, we're told he went to Buffalo, New York. He showed up, got off the train, and went to an electronics shop and purchased 12 radio tubes, vacuum radio tubes, and some wire, and went to his hotel room, constructed his project box, and secretly installed it without Peter Savo knowing what was inside the project box. Well, everybody just assumes they were radio tubes because either Peter Savo made that wrong assumption, or Tesla misguided him by saying that's what it was, that the aerial on the back of the car, the 2-meter high aerial, was to receive energy that he was broadcasting from somewhere. Anything to mislead Peter. Trust me, Tesla never confided in anyone. He kept his secrets to his chest and took them to his grave if he had to. So don't believe the details of the story, but that doesn't mean the story lacks credibility or is a hoax, as Wikipedia claims it is. The title of the article is Tesla's Electric Car Hoax, something along those lines. Nikola Tesla's Electric Car Hoax. That's what they call the title of their article. And I take the position, it's not a hoax because it's based on rumor. If we had evidence that it's a hoax, then it's a hoax. But when we lack evidence, all it is a rumor. Gossip. Gossip Mill has created a rumor. And Tesla may have been the one who started it. Regardless of who started it, although the article claims it was Peter Savo, the common knowledge, the common presumption is that Peter started it, because we don't know if Tesla started it or if he gave Peter the facts. I'm assuming Tesla started it to misguide Peter and the rest of us, because he knew Peter was a blabbermouth and would spread it around, so might as well give him false information. So I suspect those 12 vacuum tubes were vacuum tube capacitors, and that he had a single supplier custom making them for him for any of his projects on demand in Buffalo. And Buffalo was the first town supplied by electricity by his Niagara Falls power plant. The very first AC power plant, hydroelectric plant ever built, was Nikola Tesla's power plant at Niagara Falls. So it's not a coincidence that he had his vacuum tube capacitors manufactured at Buffalo, New York. I'm guessing. That's speculation according to Vinny. All right? But then I think it's actually in the article on Wikipedia about vacuum tube capacitors that he was the inventor, and they did not become commercially available until 1942, which is a year before he died. So you can spin that any way you like. Conspiracy theory version, or how, why did it commercialize a year before? You can answer that question yourself. Nobody knows. So let's see. So I focus on these three components, and if I can not shake my camera hand, there we go, to give us an output, and it's a very interesting output. First of all, I might as well warn you that nothing is as it seems. Everything is in Alice in Wonderland, Through the Looking Glass, reverse image. Whatever you think is normal is going to be inverted. It's the most bizarre, this is the most bizarre circuit, but I did succeed at one thing. I did not succeed yet in establishing a regulatory self-oscillation so that I have a window parameter of a maximum and minimum of my peaks and troughs of my waves, so that my RMS is steady and doesn't climb to infinite oblivion. Unfortunately, that's still an unsolved mystery. But I did manage to get current to rise, so that now I have a substantial amount of current relative to my voltage. I still have voltage dominating, I think, most of the time, although that may not be the case for all of these 5 components that you'll see in a minute. But be that as it may, I did substantially raise the current, so now we can call it a circuit synthesizing electricity instead of simply a transformer raising voltage at the cost of depleting its current, because that's the way a Tesla coil works. But now this does not. This actually amplifies the watts, the power, by increasing both volts and current, as we're going to see in a second. So let's move right along here. So what are we looking at here? We're looking at the wattage of coil number 1. All right? So coil number 1 is this darn thing over here, and that's I consider to be a load. These 2 coils are loads. So if we look at the wattage of those 2 coils, What we're looking at is a hyperbolic curve or an exponential, let's leave it at that is starting at 0 and going up to what looks like around 8.5 to 9 terawatts in 6 seconds. All of these tracings are 6 seconds duration. And that's another thing I might as well repeat that's worth repeating. A simulator simulates according to the time frame, well, at least in microcap, the time frame, the maximum time frame that you set. And that setting of maximum time actually turns out to be a variable, a parametric variable that's going to influence the outcome. So if you change that, the thing may go flat on you, and you think, no, wait a minute, that doesn't make sense. Why are there nodal points of time duration? There shouldn't be. Well, under conventional electronics, that's the case. But microcap, along with all the other simulators on this planet, I can assure you, were never designed to study over unity. They ignore it. Doesn't mean over unity does not exist. But see, this is the kind of social engineering that goes on. You go to be trained in the colleges, and you take your lab work. You go into the simulator to do your lab work, and all of the simulators are going to steer you clear of over unity, because that's what you're going to be told by the professor lecturing to you. And so your simulator does the same thing. Ignore and deny that over unity exists, that electrical reactance can give you over unity, or make energy disappear for that matter. It's just going to ignore the topic. So you're not going to find simulators oriented this way, and so you're going to get weird answers that don't, or weird experiences that don't make sense. It only makes sense if you presume that they're not supposed to make sense. It's supposed to confuse you so that you steer away from that. But I know better, because I've spent all my time learning from a simulator. I've never learned from anybody else. Anything I quote, if you don't like me quoting Eric Dollard, then forget about it. Ignore it, because I only use my quotations, my citations of theoretical referencing to at least give me some clue as what's going on here, because the simulator doesn't tell me. The simulator doesn't know what physics means. It doesn't know quantum physics. It doesn't know about counter space or the ether. All it knows is mathematical formula that we tell it, plus sometimes policy, unfortunately, gets written in there. But when we get nothing but mathematical formula for the most part, it's teaching me the basis of electrodynamic theory without the bullshit and without the avoidance of the hot suns, the anomalous hot topics. So then I have to go to people like Eric Dollard or Peter Lindemann or Aaron Murakami or Jim Murray to try to explain this phenomenon, because if I go elsewhere, I'll get answers, but they won't make any sense. They'll be as bad as not knowing in the first place, because it'll be gobbledygook, you know? It won't make sense to the common layperson like me. I'm a common layperson. So I have to go with people who make it their job to focus on over unity, like Paul Babcock, all these people. And so they're the ones to listen to, because they're the only ones who knows anything to describe this phenomenon. Tesla didn't tell us theory. Oliver Heaviside, okay, if you're an electrical engineer, you can make sense of it. But I need something in lay terms that I can make sense of. So that's the only reason why I go to these people, because they believe, they understand, and they can create over unity if they want to. Doesn't mean they will for your benefit. It means they have done it, and so they know what they're talking about from experience. And that's the kind of person I want to listen to. Somebody who knows what they're talking about from experience. So yeah, the outcome, I didn't spend any time kind of to try to bring the values of output of this circuit to a more reasonable level, because it does, well, this is reasonable. Tera in 6 seconds, that's not bad. Now maybe it could be better, obviously, but the fact that it's not 6 nanoseconds, that's a big improvement. I have the toughest time sometimes trying to elongate, slow down the rise to infinite oblivion, so that instead of taking nanoseconds, it takes seconds to reach a ridiculous value in which, yeah, Tera, your circuit, it's burned up by this point. Because if you slow it down, then you could do what I'm thinking Tesla did when he did his Pierce Arrow demonstration. There were no motor controllers in those days, no microchips controlling the operation of the vehicle. So he would literally have to use his manual foot on the accelerator pedal, pulsing it on and off, to get an RMS value that the motor could live with. That's what I'm guessing happened, okay? Because I don't know how else he could do. Knowing what I know about these kinds of circuits, I don't see how else he could have done it. He might have had a flywheel, a nice heavy flywheel installed. That would help, you know, so that when he pulses it, he's just pulsing or keeping the flywheel going. And meanwhile, the car might be stationary and the flywheel is still going because he took it out of gear, put it into neutral in order to come to a stop. So he would have had a manual transmission, and he would have been pulsing the accelerator pedal, and he would have had a heavy flywheel on there to help produce the results that he would want to see. That's my guess. Maybe you'll come up with a better guess. So these are the watts, and they're in terawatts, but still, moving right along. So this is coil number 1. Now this is the voltage. Now notice the triangle waves, and the RMS value is going. These triangle waves shows me that it's capacitive reactance that's dominating. And this is a coil giving us triangle waves. You know? Normally coils give us sine waves. Now if you match up all of the images, you'll find that something else weird happens. Under certain circumstances, depending on the component, I believe, I forgot to do one thing. I forgot to do phase relation diagrams. I'm sorry. Because I forgot by now which ones are out of phase. So let me give you a heads up, since I don't have the schematic in front of me to show you. Either the caps or the coils are locked in phase, so that there's zero difference of phase relation between the current and the voltage for that component throughout the circuit. The other one of those two types of components is reverse of what it normally is, and I believe it's the inductor. So I think the caps are in phase while the inductor is out of phase, but in reverse. I think it's called a negative inductor, in which normally an inductor, when it's doing its thing, wavy sine waves coming out of the inductor, the current lags the voltage by 90 degrees, but in this case it's the opposite. It behaves like a capacitor, in which the voltage lags the current by 90 degrees. And it's triangular waves. That's the bizarre, from memory, on dim memory, I believe that's what happened, what I found to be the case. Be that as it may, you'll get to find out on your own. How's that sound? Get to do a little of your own matching, and you have to play with it, because when you put them together. Oh, and that's another thing. Whether or not the voltage exceeds the amperage, or the amperage exceeds the voltage, also does a little flipping and flopping and twist and turning, something other than what you would expect when you start to study these 5 different components. This is really the most bizarre circuit I've ever seen in my life. It's disgustingly bizarre. Okay, let's not knock it too much. It's free energy, huh? Come on, don't complain. Now this is the current. This was the voltage. Now we're looking at the current. Still triangular waves and still on coil number 1. Now we're looking at the watts on the aerial. And the wattage on the aerial is minuscule. It's like, what is it? It's probably 6e to the 20. Oh, excuse me, it's not minuscule. Sorry. No, it's 6e to the 22. So the wattage is humongous. Is it getting it from the aerial, from the ground, or from the air? No. How could it? It's putting it out in a positive ionization in this case. Well, this is RMS, so no, forget that. Whatever the polarity is, actually it's going to be both positive and negative. So it's putting out a humongous amount of wattage, and that's going to disrupt the environment. So you're going to have to deal with that, or have the FCC at your front door. Okay? Rule number 1, do not anger the FCC. Now, on the aerial, it's the voltage that's humongous. And it is both positive and negative. And it goes less than absolute value 3e to the 17 spikes of triangular waveforms. Now this is the current. Now the current is minuscule by comparison. This was e to the 17, and this is e to the 5. So it's less than 500,000 amps are these triangular waves. Now, oh, we saw that already. Now we're looking at capacitor number 3. So if we go back to the schematic, capacitor number 3 is this one up here, okay? Within the octagonal arrangement. And this is the wattage. Now the wattage, you'll notice, is a little less than what the aerial was. This is e to the 17 instead of e to the 22. Yeah, it was 22, wasn't it? Yeah, 22. So the aerial, the wattage was, 22 digit positions to the left of the decimal point on the aerial, but on capacitor number 3, one of the octagonal capacitors, we've got 17 place values to the left of the decimal point, giving us the RMS, or the wattage, of the output. And now this is the voltage on capacitor number 3, and it's in the gigavolt range. So this is the one in which the amperage exceeds the voltage. This is the instance, and you don't get a nice wave. You get this weird thing that can't make up its mind what it's doing, and then the nice curvy RMS. Now when we move onward to the current on the capacitor, the current is stable. That's the one thing I did manage to do, is a stable current on the octagonal capacitors. It's triangle waves, and the peaks and troughs are slightly randomized. They vary a little, but only a little. The overall is the same, and so your RMS is going to plateau at less than 1.5 megaamps. That's your capacitor. Now we move on to the inductor, L29. That's one of the octagonal inductors. The wattage is rising, and at 6 seconds, it's less than 240 gigawatts on the octagonal inductor. Now the voltage, the voltage is rising. They're triangle waves and they're rising, and at 6 seconds, it's less than 100,000 volts peak to peak. Now the current is stable on the inductor, and it's something less than, the peak to peak, or the RMS for that matter, is something less than 6 mega amps. Now let's go back, but first let's make note of the fact that the octagonal inductor is stable amperage, okay? On the octagonal capacitor, same thing. The current is stable. So on all of the octagonal caps and coils, the voltage is rising. It's doing this. But on the current, it's stable. So you have stable current with rising voltage. Does that make any sense? No, I don't think so. Okay, now this is cap 1. So cap 1 is over here. And here's cap 2. So cap 1, the wattage, no, excuse me. Whoops. Well, no. Actually, again, nothing is as it seems. So on cap 1, the current is rising exponentially, as if it were the watts. And at 6 seconds, it's something less than 1.6 giga. Oh, no, excuse me. No, this is the wattage. I'm sorry. No. And wrong answer. Okay, the wattage is exponentially rising, and in 6 seconds is something less than 1.6 gigawatts. Now we look at the voltage. The voltage is rising. And what happened to the current? Oh, here's the... Oh, they're both. Both the voltage and the amperage. So here's the voltage on cap 1, one of the load caps. And the voltage is rising. And then we look at the... So, let's see. The voltage at 6 seconds is something less than 24,000 volts. Meanwhile, the amps on cap 1 at 6 seconds is something less than 240,000 amps. So that's how we managed to get less than 1.6 gigawatts on the cap. So the cap load, being that it's a higher farad than the octagonal caps, obviously it's going to be a less value of wattage. So we have something less than 1.6 gigawatts on the cap load. Meanwhile, on the coil load, it's something less than 10 terawatts. So the coil loads over here, top and bottom, the coil loads are able to tolerate a lot of, at 1 unit of capacitance, can tolerate a lot of load. And it has a lot of energy to provide, while the caps have far less. That's what it looks like, right? The coil has terawatts. Meanwhile, the cap load is gigawatts. So that's an order of magnitude difference of 1,000. So the coils can tolerate 1,000 times more load than the caps. That's basically what it's telling us, per unit of farads and henries, or henries and farads, I should say. All right, this completes this little discussion or monologue, and I guess here's looking at you, kid.